So hello everybody, welcome to the last of the online meetings for multivariable calculus, MTH218. So I just want to continue where I was last week. So last week we were looking at revision. I mentioned a bit about overview of the exam, formal machine, looked at flux integrals, so going backwards, which is hopefully helping you for your um, last online assignment, which is due the end of the week, which I see a few people already done and some have got full marks already, which is excellent. So I just want to keep going backwards. So what we're up to was looking at line integrals. And so I've got time, we'll do multiple integrals and quartics. So I won't do every single question I've got listed here. Okay, so looking at line integrals, so I think I mentioned some of this the other day, but I just want to just go remind ourselves. So with line integrals, this is my suggested strategy. So if you've got a vector line integral around a closed curve, so closed is the key thing here, then use either Stokes' theorem if you're in 3D or Green's theorem if you're in 2D. If it's not closed, but the vector field is conservative, so you've got a vector line integral, then using the fundamental theorem of line integrals works really well. If neither of those two happens, then you can't. Then they're the most powerful theorems. But sometimes you've got a geometric result, so maybe if you're looking at length of a straight line or length of a curve, that might make it easier. But really, you really have to do parameterization, which isn't too bad. It just integrates by substitution. There are fancier ones, like closing the loop and using Green's theorem, but last week people weren't so keen on that, so it's mentioned there. But those first four are certainly sufficient. And again, you never need to use geometric results, but sometimes it's useful to pull them out to make in other sort of integrals easier to do. So using them often can make things easier, but it's not compulsory. So here's a bunch of questions. Let's just take a snapshot. So a bunch of questions. They're going to work. What we're going to do is we're going to work out the different sort of strategies you might do for all these different integrals. And then we'll have a go at some of them, but not all of them. So the first question here is from one of the tutorials, so you might have done it. So we've got a vector line integral. So we've got f dot dx, it's the vector one, given a vector field, and we've got a parabola. So my thinking, is it closed curve? The answer is no. So you can't use Green's theorem on a parabola at first glance, and not really in any, even at second glance, it's probably not very nice. So you're going, well, is it conservative? Checking for that. So how do you check if something is conservative or not? Well, you write down the two components P and Q, if it's a 2D one like here, or R if it's a third component. And then what we really want to check is just do the swap the derivatives. So we want to do QX and PY. Now these ought to be the same if it's conservative. Now if it's a three-dimensional vector field, so three components, you'd have to use the curl in general to work out if it's conservative, but for a 2D one like this, just take QX and PY. So the partial derivative of Q with respect to X is keeping one of them constant, X constant, times by the derivative of the other one. So sine, say that again. So keep X constant to multiply by the partial derivative of the other one. So sine of X, Y, well, the partial derivative of that one will be cos XY. And then we have to, using chain rule, multiply by the derivative of what's inside. So the partial derivative of what's inside is just y. In the same sort of way, the partial derivative of y sine xy would be y cos xy x. It's completely symmetric. And we can see these two are equal. So therefore it's conservative. And therefore we can use the fundamental theorem of line integral. So how about I'll do this one fully. Just to remind ourselves of how to do this sort of stuff. Okay. So now I know it's conservative. The real heart to this question is to try to find the potential function. So what we're trying to do is we're trying to find a scalar valued function, it's the potential. So we're trying to find f, which would be a function of x and y in general. And we know that if you take the partial derivative of it of respect to x, we get the first component. And if you take the partial derivative with respect to y, we get the second component. That's what we're trying to find out. And we want to write them, spell them down explicitly. And so P here is the y sine xy. And so what you do is just pick one of the equations. So I've got fx is y sine xy, and I just want to integrate it. So I just want to integrate it with respect to x. Now, here I'm integrating with respect to x. So the y at the front here is just a constant, so I don't have to worry about it. So it doesn't make it, doesn't mean there's no parts required or anything like that. So it's really integrating sine xy, and that's just a function with the insides linear in respect to x. So I can use reverse chain rule. So reverse chain rule says the integral of sine is going to be minus cos xy. And then I have to divide by, using reverse chain rule, divide by the derivative of what's inside. So the partial derivative of the inside with respect to x is y. You can see the y's cancel out. You're left with minus cos xy. Now, I haven't quite done it all. Whenever you're integrating, you can get a plus a constant. Now, that constant is constant with respect to the variable we're integrating with respect to, so it has to be constant with respect to x. But it can be a variable of anything else. So it can be a function of y's. So we've worked out one part of f, but we should need to keep going to work out what the rest of it is. And so what we need to do is take the partial derivative with respect to y, and then we can bring this second equation to bear on it. So taking the partial derivative of this with respect to y gives you minus x, so positive x sine xy, using the same sort of ideas as before, plus k dash y. But we know that's equal to q, right? That's what this equation says. So f dash y equals q, and so q is x sine xy. You can see those two match up, and so what we really left then is that the derivative of this k respect is equal to 0, and therefore ky here is not a constant just respect to y, but it's just any old constant. So a constant, just a constant respect to x and y. And so we can pick f here to be minus cos xy plus any old constant. Now, because we're going to plug it in and do differences, the constant really doesn't make a difference at all. And so without loss of generality, that's what log stands for, we can take k to be 0. So multiply that's equal to 0. And then what we're allowed to do then is that the integral of the gradient of f, which is what the capital F is, dot x, from a to b, then by the fundamental theorem of line integrals would be the function of f at the endpoint minus the function at the starting point. So we should work out what these things are. And so if you go to the question, the endpoints are 318 at the end, and the beginning is 1, 2. So just sub those in. So 318 minus 1 and 2. So just plug them in and you go for it. So if you plug in 3 and 18 into minus cos xy, you're going to get minus cos 54. Sub it into this one, you're getting minus minus, so positive cos of 2. And that's the answer. So that's the fundamental theorem of line integrals. So that works really well, or works exactly, precisely when you've got a conservative function. And therefore, when I'm doing it, I would check for those. So check for close first, because Green's theorem will pick up anything that's conservative when it's doing it. So close is easier, but if it's conservative, go for that way. So let's do the next one. Oops. So another one from tutorial 8. So I mean, why I've done these two is in particular, is people requested them. So um, um, people had tricks, had trouble with them. So I thought I'll do these ones in particular. But I've got a few others there that I've mentioned. So this is another vector line integral. So we're integrating on the right hand side of a unit circle, starting at 0, 1. So I've got a circle then. The right hand side would be this thing here. So it starts at 0, 1, and I guess finishes at 0, minus 1. Now, first thing I ask myself, is it a closed curve? The answer is no. Next one, is it conservative? So again, it's 2D, so you do P and Q. Py, in this case, is 1. Qx is minus 1. Now, these are not equal this time, so therefore it's not conservative, so I can't use either Green's theorem or the fundamental theorem of line integrals directly. Now, you can do tricks, so you can close it off. So you could put another curve in here to close off and do Green's theorem, but I won't do that. So the normal default option really is to use parameterization. So you have to parameterize it if you don't want to do tricks. And so you're going, well, it's a circle. And so for circles, really it's x is equal to r cos theta. So the radius, which in this case is 1, cos theta, and y equals radius r sine theta. That sort of jumps out to you straight away. Now you think what theta is going to be. So theta. Now normally circles are anti-clockwise, but you go, hold on a sec, this one's not anti-clockwise, this is clockwise. So the trick with this question really is it's going backwards. And there's more than one way of specifying it, but a way what I find easier, because you can do it with integrals, is just to write the limits in reverse order. So the top here is when the angle here is pi on 2. So really going from pi on 2, and we're going then decreasing it all the way down to minus pi on 2. Which is in reverse order, of course. I mean, you start the biggest, going to the smallest, and that just indicates that we're doing them in reverse order. And that there is a sufficient way, so to try to indicate what we're doing here. And then when we're trying to do the integral, so therefore we need to work out what the differentials are, so you can plug everything in. So doing differentials, dx would be the derivative of cos with respect to theta, which would be minus sine theta d theta. And dy would be the derivative of sine with respect to theta, which would be cos theta d theta. And so our integral is the integral of p dx plus q dy. That's what we're trying to integrate over along the curve. And basically we're just going to substitute everything. So integrating from pi on 2 to minus pi and 2. So just by putting the limits in opposite order to what naturally is, just means going clockwise rather than anti-clockwise. Y then becomes sine theta. Dx becomes minus sine theta d theta. Q is where it is. Q is, should write it down, shouldn't I? Q is minus x. So that becomes minus x, which is minus cos theta times by dy, which is cos theta d theta. And so if you see it, you go, well, you've got a minus sine squared minus cos squared, and they just become, if you add up those two, you get 1. So you can equal from pi on 2 to minus pi on 2 of minus 1 d theta. So minus 1. And when you're integrating that, just becomes the length of the interval. So minus of minus pi and 2 minus on the pi and 2. And after some simplification, you're getting pi is the answer. So some things why this question, I suspect someone asked this one in particular, is when you can't use Green's theorem or fundamental theorem of calculus, parameterization is the way to go. And there's a few standard parameterization like straight lines and circles here. But just be wary that for a circle at least, the standard parameterization is anti-clockwise. And you have to do something to handle the anti-clockwise. And that was my little trick here, just by putting the limits in reversed order, will make it go backwards. There's other ways, but that's I think the cleanest in terms of writing on a piece of paper. Okay, so that's 2 examples. Let's look at strategies for other ones. We won't, and if you want me to do any, just yell out. At the moment I'll just do the bottom one here, but I just want to talk about the other ones at least. So you've got another vector line integral of a 3-dimensional vector field this time. And we've got T is the boundary of the triangle with certain vertices. So if I try to draw the picture, the 3 vertices are there. So it's a triangle sitting like that, if you can visualize it. So it's sitting in a slope sort of triangle. And we're trying to work out the vector line integral around this curve. And it doesn't say, but it does say traversed in that order. So it does give an ordering to it. First of all, I go, it's a closed curve. So as soon as it's a closed curve, I would think I'd use something like either Stokes or Green's theorem. Now, because it's sitting in 3-dimensional, so it's sitting in 3 dimensions, I would use Stokes' theorem for this one. And with Stokes' theorem, I then, therefore it's an integral over some surface, which that is the boundary. You might as well put the solid triangle, and the solid triangle would have, be a certain predictable plane. If you look at it, it'd be x plus y plus z equals 1. The unit normal would be 111 all over root 3, etc. So you could, because it's a plane, you can work out normals, etc. fairly easily and go from that way. So Stokes' theorem is my suggestion for it. Now, if you don't like it, you could do it parameterization directly, the 3 different parts, but that's one way of doing it. And again, if you want me to go through the details, just ask. But I want to get other things done if that's okay. Next one is another integral, another vector field, this time over a triangle sitting in 2D space. So again, it's a closed curve. And so I would use, because it's in 2D space, I would use Green's theorem this time. And so because it's 2D, there's a lot of things to worry about. So greens certainly is the quickest way of doing this one by a long shot. Stokes requires you to understand surface integrals, um, which um, some people are a bit more hazy on than others. So you've got to make a decision. In the exam situation, can you do Stokes theorem, so do a surface integral or three different line integrals quicker? For me, I would certainly use Stokes theorem. I find that easier, but you've got to make the decision yourself what you can do. Do you want to do this last one? So I'll do this one explicitly. So this one here is a integral of x ds of a curve. The curve part's missing, obviously. Now, notice this one's a little different to the last few, as in it's got a ds here. So that means it's not a vector line integral, it's a scalar line integral. And so therefore you can't do things like Green's or Stokes or fundamental theorem of calculus. None of those apply. And so you might get away with some geometric results occasionally. So, but if you look at the curve, that's the curve we're looking at. Um, that doesn't look like anything that we would recognize off the top of our head. And so we really are forced to parameterization. So let's try to look at this one. So parameterization really is the only way to go. And so some things that we need as preliminary stuff is we need to work out some derivatives. We'll need these in a second. So dx dt is equal to 1, dy dt equals 2t, and dz dt is 2t squared. So we've got the different derivatives. So the key thing with substitution really is, so that's what we're going to do. So just parameterization. The parameterization is straightforward. It's given to us in this question. It's just a matter of using it. So in order to substitute things, x is going to be t, that's okay. We need to work out what ds is. And you can, on the example formula sheet it's written down, you need to know what it is. So either just copying it from your own formula sheet or otherwise. So it's a square root. So depending, it's the length of the vector of all the derivatives is the one way of putting it. But it's basically this get each derivative, square them all, add them all up, and take the square root. That's the main component, and then it's still a substitution. So we're going from ds, so it's d of a small bit of arc length to a small bit of the parameter. So we're going to work this thing out. This is the key thing with substitution. This is, and often can be quite difficult. This is where it can be tricky. So dx dt, that's going to be 1 squared. Dy dt is going to be 2t all squared, so 4t squared. Plus dz dt, so 2t squared, and we're going to square that one, so that'd be 4t to the 4 dt. And so our integral now becomes the integral from the limits of the parameter, so 0 to 1. X is going to be t times by the square root of this thing we just worked out. So what we've done is by using parameterizations, the obvious one given in the question, we've converted the line integral into just a normal 1D integral in theory that we know how to do. Any ideas how to do it though, I guess? Can anyone give me suggestions of how to actually do that integral that we've managed to produce in this case? Any ideas? Okay, that's okay. Oh, someone's got a brainwave. So when faced with an integral like this one, the things that cross my mind is going, well, maybe I can do substitution. You're going, well, what's really what the real problem is here? It's fine. You could have kept typing. So what the real problem is here is that what's under the square root is what's difficult. So if I could simplify that down, um, that'd be the way to go. So trig substitution, um, they sometimes work. So trig substitutions work really well when you've got um, a difference of two squares under the square root. That's when they really work well. When you've got a sum of two squares, you can use some. Sorry, turn that down. If you've got a difference of two squares, then you'd use cos or sine. If you've got a sum of squares, you use sec. So you'd use your sec or tan. That's sort of obvious substitutions. Here you're going, well, I've got three different components, so I have to do something else. So I like what someone else wrote there, but this is how I would think to do it, is to go, I would try to simplify what's under the square root. That's really the hard part. And I go, well, if I look carefully, then I can see this is a 1 plus 4 times by u, say, we use t squared, plus 4u squared. That's what underneath the square root really is. And if you look at this, that's just a quadratic. So underneath square root is really a quadratic in t squared. And I can factorize that. If you look at it this way, in particular, I can say, oh, hold on a sec, that's just a perfect square. So that ends up being 1 plus 2u, or 1 plus t squared, all squared. So that's what underneath the square root really is a perfect square. And so as soon as I see that, then I can, the square root of a square just cancels out. So it's 1 plus 2t squared. Technically, it should be the absolute value of it, not that it matters in this case because it's already positive, dt. And so, as someone suggested, letting u equals 1 plus 2t squared would indeed work the problem out completely. That's exactly a good idea. But so you can see, it's difficult at first glance, and you go, let's try to simplify that. So if what was underneath the quadratic ended up being a sum of two squares, so to speak, then yes, some sort of some sort of tan or sec might work if it's a difference cos or sine work, but you've still got the t at the front to worry about. So just trying to simplify is the key. From here, you could do the substitution. I think just going to be easy in this case, just to expand it out. And then now it just becomes a straightforward integral to do. So t squared on 2 plus t squared on 4 on 2, put in 0 and 1. Sub in the 1s, you're getting half plus half. If you're 1, sub in 0, you get nothing. And so the length, so the average x value along this curve essentially is equal to 1. That's what we've just worked it out to be. So that's a line integral over 3D. So I thought I'd just do that example to a 3D one. So, but if you had to do a 2D one, same sort of things applies. The difference often is for 3D, this component here can blow out in complexity even more so. So I thought I'd just do that harder one to give you see what that one looks like. But it's the same approach. So the strategy is exactly the same. It's just a matter about taking your time to think through how to do the integral. Now, if I ask this in an exam situation, by the way, then the going from the bottom, so from here onwards, really is about methods you've been assessed in previously. Now, it's still important for this subject. So most of the marks for this sort of question would be in setting a problem up. That's where most of the marks would be. There's to be a little bit, there'd be some, but certainly definitely less than half would be the bottom part, because the things I really want you to learn in this subject is how to go from a vector line integral and understanding it. Sorry, how to go from a line integral, scale in this case, and understanding it and breaking it up to the parts. That's the key thing I want you to be able to do. This is still useful in the context, but not as important. So therefore, if you get a question like this and you go, oh, it's too hard, at least start it, because you still get lots of marks. Even if you get to that stage and got completely stuck, you still can get most of the marks. Okay, so that's some things on vector line integrals. Now we've done other things. So just going back in the subject. So the last third of the subject was vector calculus. So I was looking at, in particular, the differentiation of vector fields, which was curl and divergence. It was looking at line integrals, so vector and scalar, and looking at surface integrals, both flux ones, which is the vector form, and surface integrals. And then looking at some high-level theorems to do lots of those. So Green, Stokes, divergence, fundamental theorem of calculus. So looking at all those sort of things. That's really the vector calculus. Then back to part 2, so going backwards in time. Before that, we looked at multiple integrals. So these weren't looking at vector fields, this was just integrating functions. So slightly different. So, and they were double and triple integrals. So most of the time we spent on double integrals, and so, and let's talk about the strategy. And you can say that when you're doing things like Green's theorem and surface integrals, double integrals, and indeed triple integrals crop up from time to time, like divergence theorem. So this is sort of a prerequisite for the vector calculus part anyhow. So my strategy to do double and triple integrals, I've mentioned it before, but I would really try to draw the region of integration if I could. If it's a triple integral, at least try to draw the shadow of it, which is in 2D. So just draw what I can. Look at what the region is, and see where I can recognize what it is. So if it's a circle or bits of a circle, then you go, oh, fantastic, I can use polar coordinates. So I'll do that. Look, that's why I would draw it, so you can see it then. If it's otherwise, I might recognize it's either type 1 or type 2, or maybe it's both. So if it's both type 1 and type 2, then you go, okay, maybe I can swap the order of integration around, etc. Now, in a really difficult case, which I haven't given any examples at all really for you, well, you could split up into a bunch of standard forms. So that's not really assessed as such. Then for each standard form, so you just do each of them as it stands. So polar coordinates, apply the polar coordinates, or type 1, type 2. And really just each of them resort down to an integrated integral. So for type 1, type 2, it's really just a matter of choosing if it's dx dy or dy dx. And once you've got that, just do the integrated integral. So if things to get stuck, so if you just try one method, you get stuck, one option is to reverse the region of integration. So reversing the limits, I should say. So instead of doing dx dy, do dy dx. And if you're still getting stuck, then you can try change a variable. And in this case, in this subject, I will tell you what the change of variables are. So let's look at some questions, and we'll look at the strategies. I'll do just the last one explicitly. So the first one, so double integral. So double integral over a rectangle. So if I draw my region of integration, that's my suggestion. So from x is from 0 to 2, from y being -1 to 1. So I've got a square, actually. So I'm trying to integrate over a square. And as soon as you do that, then it's both a type 1 and a type 2. So you can do either. And so it's just a standard, it is just a standard format already. And it just matters doing it directly. And because it doesn't matter which one you pick, x or y first, really. And if you look at the limits, I would integrate the y1 first. So I would do dy dx. And my main reason for doing that is because I'm integrating between -1 and 1, which is an odd. So, which is, I can use things like odd and even functions to help me out. That's why I would pick that one. But if you do the way around, it's okay. So that one's a simple one, really. That's just one of the easier ones we've done. Next one, Another integral over a more complicated region. I'm going to try to draw it more carefully. X and y is greater than 0, x squared plus y squared is less than or equal to 4. So therefore, that's just a circle, the radius 2, and we're considering x and y being greater than 0. So therefore, the region that we're considering then um, is this bit of a circle. So what we have here is a bit of a circle. So this is a quarter of a circle. So what method would you use to integrate this region? How would you integrate that? What method would you use to try to do this double integral? Yep. And as someone suggested, you try polar coordinates. And so when you'd end up doing is integrating dA would be r, dr d theta, and you'd do the limits of r would be from 0 up to 2, it's a circle radius 2, and theta would be from 0 up to the top angle, which would be pi and 2. And then when you've got it as an integrated integral, just go from there. So as soon as you see bits of circle, polar coordinates. That's which is why I think it's useful to draw a region. 3 and this one are the same, so let's just do the bottom one here. So I've got an integral 0 to 1, 3y to 3 of e to the x squared dx dy. Now what you do is you go, well, it's already written down in normal format. Just try it as it is. So I'll just try integrating the inside as it is written. So you know, what's the integral of e dx squared with respect to x? You go, that's hard, really hard as a matter of fact. I'm not sure if you realise, but it's actually in a non-elementary, has a non-elementary answer, which is code for very difficult. So as soon as you go that, you go, well, that's just going to be too hard. Maybe not to try to change things up. So a trick then would be I need to either do polar coordinates, reverse the region of integration, or do some other fancy substitution. Now they haven't told me a substitution, so I don't think it's going to be that one. So polar coordinates or reverse the limits are the two main strategies we've learned. The key way to work out which either of those two should be appropriate or how to go proceed really is to draw the region of integration. So if you look at this, the inside limits say that x here is between 3 and 3y. That's what the inside limits tell me. And then but otherwise y is between 0 and 1. So I draw my picture. So x is equal to 3 is that sort of straight curve. 3y equals x is the other boundary curve, or putting it the other way, y equals x on 3. That one's y equals x on 3 is my other bounding curve. And I'm going from y equals 0 up to y equals 1. And if you notice, that ends up being where the 2 points meet, the two different curves meet up. So if you make it equals 3, you get y equals 1. And so, therefore, the region I'm integrating over is that sort of triangle there. I can't remember it's highlighting for some reason. And so it's not a circle or bits of a circle. So polar coordinates don't really scream out to me as going to be really helpful. So I won't try polar coordinates. That probably isn't going to help. And so what I'll do and try to do instead is try to reverse the order of integration. So we've integrated dx dy. So let's try and change around to dy dx. So what we need to do then is instead of thinking of as going that way between two different functions of x, we need to swap around to being between two different functions of y instead. So as you can see in my picture, I can see as I've already drawn it, the highest y gets is the line y equals x on 3, and the smallest it gets would be the bottom here, which is the x-axis, which is y equals 0. So I can put those limits down. And then I need to work at limits for x. And again, they're from the picture. Smallest x gets is 0, biggest it gets is 3. So I can put those down. And now once I've got that, now hopefully it's easier to do. So with the integrated integral to the inside first, so integrating e dx squared with respect to y, well, that's all right. Integrating with respect to y is straightforward. There's no other y's present, so at least the inside bit's easier. Subbing my two limits, subbing in 0 gives you nothing, that's all right. And so we're getting x on 3 e dx squared dx. Now hopefully I can do this one a bit easier. So how do you integrate this one here? Now it's just a 1D integral. How would you approach this one here? So we did this to hopefully make it easier. Is it really? Any suggestions for what to do? Yeah, some suggestions, good. So you can try integration by parts is one idea. Or you can do u equals x squared. So if you integration by parts, you would you can't really integrate e dx squared, so that's probably not going to help. So I think integration parts probably is not going to be very helpful. But u equals x squared certainly goes a long way. So letting u equals x squared is a good idea. Someone else might have a different idea. There's often more than one way of doing these things. And so since x was 0, the new limit would be 0. When we've got 3 would become 9. We've got x on 3, e to the u, and dx would become, so du is equal to 2x dx. So the x and the dx together become a du on 2. And so we're getting 1/6 integral from 0 to 9 of e to the u du. Integral of e to u is just e to the u from 0 to 9. Subbing the 9, get e to the 9. Subbing the 0, get 1. So more than one way of doing it, of course. But you could, so that's my approach at least. But nevertheless, when you get to this stage, what I'm thinking when I see it, here I've got a function of a function. The inside function is x squared. The derivative of that one is something about x. And I have an x out the front. So therefore, integration by substitution really is going to be beneficial. Parts is good for products. But if you think about it, you've got to make sure, if you do apply parts, you're trying to make it simpler. So you're going to do a parts. You can't integrate e dx squared because you don't know how to do that. So you have to differentiate it. As soon as you differentiate it, you get another x term. If you got this one, you're going to get increase the power. So by parts would just increase the polynomial at the front of it, which is not going to be very helpful. So therefore, integration by substitution really is the way to go for it. So it's fine. Mistakes are good, right? You'll learn from that. So, but it's good to think through the different implications of it. And again, if you tried something, I mean, just like here, we tried the very first approach and got stuck pretty quickly. If you get stuck, just swap over, try something else. That's the whole idea of problem solving. This other question I got is similar, but I won't do that. So you can see it is important to be able to know the strategies and be able to try a few different things. So we did lots of those sort of stuff. I haven't got an example of change variables here, but that's important. Um, at least it'll be told to you, so at least it'll be obvious when to do it. It's just a matter of going through the process. The key thing with that, just want to flag it, is people often forget the Jacobian or get it run the wrong way. So just pay attention to make sure you put that in. And also make sure it's the absolute value of it. That's also important. Okay, so going even back further. So topic chapter 1, that's the very first thing we did. We looked at basic partial derivatives and some things related to that. So things like tangent plane, gradient vector, approximations, directional derivatives, that sort of stuff. In the main, I think people find that okay, but again, you got to work it out yourself. We also looked at lots of different curves and surfaces. I think people find that a bit harder, so that's one I want to comment on. So in particular, the curves we looked at were circles, straight lines, they're not too bad. Other conics, ellipses, hyperbola, parabola, they're a bit harder. And so knowing some key features of those is important. Then if you jump up to surfaces, we looked at planes, okay, spheres, okay. Then looked at lots of the other quartics. They get really messy, but they're really important. And so I want to look at some of those aspects by doing a bit of a harder question to finish our time off. So just dealing with these things, by the way, if you want to work out quartics, really, so if you got to try to, if you're looking at surfaces and quartics are a common way of doing it, then really to classify any surfaces, you've really got to break it down into its components. So using traces, that's basically using fixing a certain values, are ways of trying to understand it. Now, the example formula sheet that I provided has lots of standard pictures. You could use those if you wanted to. So you certainly need to be able to do rough sketches of things. And so if you go, oh, I know it's a elliptic paraboloid, you can draw the picture of an elliptic paraboloid and then put the axes and label things afterwards. But often draw the picture first is a good way of doing it. Okay, so let's look at this harder question. Okay, so I've got I don't have a surface. I've got a conjugated function of 3 variables. So a function of 3 different variables, x squared minus y and y squared plus 1. And I want to try to understand it. Now, if I was trying to draw this, I'd have to say w is equal to this. And so it's ends up being sitting in 4-dimensional. So it's a bit hard to get a real handle of what it really is. And so to try to get a sense of it, I've got to drop down the dimension to make it easier. And so what I'm going to do is I'm going to think of level surfaces, which is what the question tells me. So level surfaces pretty much are saying, I'm going to get my function, and I'm going to make it equal to a fixed value, k, say. And I'm going to consider different values for k. So -1, 0, 1, 2, whatever it might be, right? So that's what my level surfaces are. So I want to try to work out what they all are, and from when I work out what all the level surfaces are, get a sense of what this is really about, all right? Just like for understanding a surface, breaking the level curves is pretty useful. And so I've got x squared minus z on y squared plus 1 is equal to k, what I have in this case. So I expand it out. The y squared plus 1 is always positive, so I don't have to worry about dividing by 0 errors or anything like that, which is nice. So ky squared plus k by expanding it. Now I've got to try to put in a form which is going to be easy to deal with. Lots of approaches again. I've got a z here, so I can just make z the subject if I wanted to. So I'm getting x squared minus k y squared minus k, which is a little bit different here. There's a constant around So I'm going to put it like this. I'll explain why I did that in a second. So um, I'm making Z the subject. Why I do that is because that's a common, close to standard form, and so you might recognize it quicker that way. You don't have to by any means, but that may help be helpful. The other thing is, it's good to try to complete the squares. So try to put down any constant term. So get rid of any linear terms with squares by completing the squares, which wasn't required here. But if there's any extra constants, just attach them to stuff. So really, I want to attach the k to the z here. So I really consider that as one linear term. So I've got one linear term, x squared and y squared. And then I can see straight away that the center, so to speak, of this one is when this thing is 0, so x squared is 0, or x is 0, when this term here is 0, so y is 0, and when this term here is 0, so minus k. So you can see the center, or the sort of the point which is acting like the origin, effectively, is 0, 0 minus k. So I can say that straight away, which just means it's moving. So there's a shifting going on there. So that's useful information to try to get a sense of it all. Now I'm going to try to classify it. Now you can see, because it's the highest term is a square there, it's going to be some sort of quadric surface. So I'm going to look at things of traces. Now I can do them more. So I'm going to have some different options here. We'll try to put them all together and then we'll pull them apart when we need to. So let's do different traces. So first of all, let's do x being fixed. So x being x naught. All right. So when x is x naught, we've got we end up getting z plus k is equal to some fixed number, right? Minus ky squared. So we've got two options. When k is not 0, we get parabola. So essentially we've got z constant, something with a y squared. So it's a parabola. And that's k non-zero. Otherwise, when k equals 0, we're getting z is equal to a constant. So we're getting z equals constant when k is 0. And it's a straight line, right? So you got that some sort of special case when k equals 0. That's some sort of something special. We can see that specially. So other sort of trace, that's option 1. We can do y is fixed. So we're getting z plus k is equal to x squared minus some constant. So we know they're constants because they don't really help with classification. We really got z is equal to x squared plus some constant around the place. And you go, well, they're always parabolas. And so since traces in two different directions are parabolas, then for k non-zero at least, that tells me straight away that we have a paraboloid. So just reminding ourselves, if we have traces in two different directions being the same type, that gives the major name. So if there was two different directions, a hyperbola would be called a hyperboloid. If two different directions, ellipses would be called an ellipsoid, for example. K equals 0 is a bit special, so I'll have to pull that one separately. Now let's look at the last direction and work at the actual special type it is. So z equals z naught. So we're going to get a constant, effectively, is equal to x squared minus ky squared. And this is going to, well, they're just hyperbolas. Well, almost. K, as long as k is non-zero. So if k is 0, then that term disappears. We're getting x squared equals constant, and so end up getting x constant. That's again, k equals 0 is some sort of special case here. So what we've got then, even if k is non-zero, these particular level surfaces are the type they are is hyperbolic. Oh no, I made a mistake there, didn't I? How about I just pull that back? I need to be a bit more careful here. Bit too quick. Again, like someone said, you've got to not rush, don't you? So there's three options we got happening. If k is positive, k is 0, or k is negative. So if k equals 0, I said x equals a constant. If k is positive, then we're getting hyperbolas. If k is negative, what do we get? Now we need to be more careful here, I think. So we're getting z naught plus k. Should just make it really careful here. So if k is negative, then we're getting x squared plus. So you got a sum of two squares. That would make it an ellipse in general. And again, you've got to be careful. It would only be ellipse so long as this thing here is also positive. So that would really require z to be greater than minus k, which would be a positive number. So it's going to be sitting up. So therefore, we've got those various options. So let's just spill it all out. So therefore, classifying the original curve then gives you three different options. So both, when k is non-zero, they're both paraboloid. So if it's k is positive, it's got an hyperbolic paraboloid. When k is negative, it's an elliptic paraboloid. And in the middle case, what's that one? Well, we have to think a bit more carefully. It's more just look at, might as well just go to the top, treat it separately. When k is 0, really all this right-hand side ends up being 0. So really you've got x squared minus z equals 0. So we can write it down. It's just going to be z is equal to x squared then. That's what it reduces to. So you can see there's no y's in it. So just all the y's disappear. So when you've got one variable disappearing entirely, it ends up being a cylinder. And because it's otherwise in the other directions, it's parabolas, it's going to be what's called a parabolic cylinder. So there's three different types. Let's try drawing it roughly, what it looks like. So I've got my different axes. So drawing in 3D is really hard. I put them on the same axes. I often do a trick of drawing the axes after I've drawn the picture. So I've got the three different cases. I know that the center here is different in each case. So it's 0, 0 minus k. So when k is negative, the center of the graph is up, is going to be 0, 0, a positive number. So that's going to be the center. It's an elliptic paraboloid, which basically means it's like a hill or so top of a hill or bottom of a big lake, and you have to work which way it is. So if you look at it, if k is negative, it's z is equal to positive, positive. So it means it's just like a nice little ditch. So it will look something like this. they're ellipses rather than circles, but that's the idea. So that's roughly speaking what it will look like when k is negative. When it comes to k equals 0, then what happens, so when k equals 0, you get a parabolic cylinder, so pretty much the y values don't really make much sense. So really it's just for different x's and z's, we're going to get parabolas. So just trying to draw my parabolas. So it's some sort of trough, I guess is what I'm trying to draw there. You can understand what I'm trying to draw. So it's just a big trough coming all the way through 3D. That's the idea. So you can see what's happening. I'll do the other one. So the last case is k is a hyperbolic paraboloid. The center has moved down to 0, 0 minus k, so it'd be just below it. That would be the center of it all. And otherwise, elliptic paraboloid looks like a saddle. And you're going to have to think a bit more carefully. So when z is fixed, we're getting z is equal to positive x squared, which means that in this direction, where's my thing gone? It's going to look like that sort of parabola. Whereas in the other direction, so when x is fixed, z is minus y squared, which means parabola is going the other direction. So set a point that way. So normally just draw the side of it. So that's sort of roughly what it is. So it's a saddle point. See, man, I'm terrible at drawing saddle points. If you need to, you could just go to the formula sheet and just copy the picture down and just center it bang just below it. But as you can sort of see, well, maybe you can see what's happening, and I can try to describe it for you, is that as k goes from negative to positive, that taking cross section, that looking at the cross sections along the positive x-axis, you always get parabolas. So you're always getting parabolas, and essentially all you're doing is just going down. So that parabola there, that parabola there, and that parabola there are all the same. It's just going down as it goes along. That's all that's changing. In the other direction, um, we had a parabola going that way. That's along the y-axis. It ends up being completely flat. It ends up stretching, opens out completely till it's a straight line, and then it starts bending the other way as it goes negative. So essentially, you've got an elliptic paraboloid, and you're opening up in one direction only, and as you're bending it open, open to a complete trough, and then you completely bend it open to be in a saddle or an elliptic hyperbolic paraboloid. So that's my bit of a summary. That's a quite hard question. Let's not kid ourselves. So you had a question of a similar difficulty in one of your assignment questions, but just showing all the different things put together. But things that I expect you to be able to do is, given to work at level surfaces or something which might give some quadric surfaces, being able to classify quadric surfaces using traces, just like I've done here, and being able to pull out the different options, and being able to do rough sketches for them in a way that you can give a rough sense of the location, like I've got here, and orientation related to the principal axis, which is what I've tried to do. So I haven't managed to capture in these pictures the sense that it's it's not circular at all. It's quite elliptical. And you can see some of them are hard to draw. And that's going to be true for you as well. So that's just giving you a bit of a rundown of some of one of the hard aspects there. I can draw some. There's some. If you want to look at pictures later on, there's some pictures of what they look like. A bit more better than what mine are. But otherwise, that's the main just a revision sort of stuff. So if you've got more questions, either right now or later, please ask by all means. So I'm around certainly up until your exam. Make sure you do assignment 4 and make sure you do plenty of revision. So please go through the sample exam and the revision questions for your own practice. But if you have any questions, fire away right now. That's fine. One thing I wanted to mention is about the survey. So I sent an email out yesterday saying I really would appreciate you filling out the survey. So you can do that by going to the Interact 2 site, if I can find it. So if you go to Interact 2 site and click on evaluation here, just click on evaluation, you can do it where you are, or you can also do it via a mobile device as well if you wanted to, for that matter. So the link I gave in the announcements, you can open up on your phone and do it on your phone. But yeah, so I really would like you to do that. As I said, I've tried a few new things this time. So in particular, I've rejiggled how I've done these online meetings. And the other thing is I've tried this online assignment. So certainly, and once you've done it, I really just like to feedback. I mean, previously it were just 3 written assignments, so I've just made that last one a little shorter and made the last bit online just so I could assess divergence and Stokes theorem before you get to your final exam, just to help people get practice beforehand. So that was the intention. But I want to see how you think how it went, etc. So just like the system or not. So there's some things I want to feedback on generally, but by all means, I mean, give honest feedback. It's anonymous. I never know who does it or not. I can see what percentage people do, but that's it. So I can't tell which ones did it, unless you really want to give your name away, and no need to do that. So yeah, please give the feedback. That would be really appreciated by everybody. So any other questions that people have? Okay. So as I said, hey, please continue to have a go at it, and I'll all the best in your exam. That's the main thing I need to say. But I'm sure I'll speak to some of you by email or discussion boards, etc., before the exam. But yes, good luck.